Welcome to The Explainer. We're here to break down some of the biggest ideas out there.
And today, we're diving into something pretty profound, right from the heart of quantum field theory. The question is, could everything we see, everything we know, just spontaneously cease to exist?
All right, so to get to the bottom of this cosmic mystery, we've got a roadmap. We're going to look at a possible crack in creation itself, we'll meet this thing called a quantum ghost, then we'll get into a wild paradox. After that, we'll check out the timeline for this potential catastrophe, ask the big question of why we're even still here, and finally, I'll point you to where you can continue the investigation on your own.
All right, let's jump right in. First things first, we need to understand the main threat here. It all comes down to this idea of a metastable vacuum.
Basically, the idea is that our universe might be in what's called a false vacuum. It seems stable, but it isn't actually in the lowest possible energy state. The classic analogy is perfect here. Imagine a ball resting in a little dip on the side of a hill. It's stable, sure, but just over a small ridge, there's a much deeper valley. Our universe could be that ball, just hanging out, not in the most stable spot it could find. So, you're probably wondering, what could push that ball over the ridge? Well, here's where things get really weird. In the quantum world, you don't always need a push. Things can just kind of tunnel right through barriers. And this is where we introduce the main character of our story, or maybe the main suspect, a truly bizarre quantum event called an instanton.
Yeah, I know. That definition looks like a mouthful, right? Non-perturbative tunneling event in Euclidean spacetime. Whoa. But let's just break it down. Classically forbidden. That just means our normal, everyday physics says, nope, can't happen. Tunneling event is the real key here. It's like the universe found a secret shortcut. And non-perturbative, that just means it's not a slow, gradual change. It's an all-at-once, sudden jump. So you can really think of an instanton as a kind of ghost in the physics machine.
Think about it. It's like a particle ghosting right through an energy wall that it absolutely does not have the energy to climb over. It just appears on the other side. And this quantum weirdness, this ability to just bypass the rules, it isn't just some little curiosity for physicists. No way. It might hold the answer to a huge physics puzzle. And maybe the secret to our universe's ultimate fate. Okay, so at this point you might be thinking, physicists just invented this terrifying idea for fun, but that's not what happened at all. See, instantons weren't dreamed up to give us nightmares. They were actually discovered because they provided this incredibly elegant solution to a totally separate problem in particle physics.
And this is where the paradox really hits you. So, on the one hand, instantons are the hero. They swoop in and solve this big mystery in quantum chromodynamics, the U1 problem. Basically explaining why particles like pions have the mass they do. Awesome, right? But the problem is that the very existence of this hero process also implies that our universe's vacuum isn't totally stable. It suggests it could just spontaneously decay into a true lower energy vacuum. So it solves one problem, but creates a potentially universe-ending one.
And check this out. This isn't just some abstract theory. There's a related process, something called the electroweak spherulon. It's a lot like an instanton, and it was super active in the crazy heat of the very early universe. And get this, it was absolutely essential for us to even exist.
Yeah, this spherulon process did something that should be impossible. It violated the conservation of baryon number. Now, why does that matter? Because that violation was the key to creating just a little bit more matter than antimatter at the beginning of time. And that is why we have a universe full of stars and galaxies and us, instead of a universe of just empty space and energy. So these bizarre tunneling events, these ghosts, aren't just a threat. They're literally woven into the fabric of our reality.
Okay, so this brings us to the big, flashing, neon question, right? If our universe can just tunnel into a new state, when's it going to happen?
Well, some brilliant physicists, Sidney Coleman and Frank De Luccia, actually sat down and did the math. They calculated the predicted lifetime of our false vacuum, and the number they came up with is just staggering. We're talking 10 to the power of 10 to the power of 26 years. That number is so absurdly huge, it's basically infinite for all practical purposes. It's a 1 followed by more zeros than there are atoms in the known universe, by a lot.
Phew. Okay, so we can all relax, right? Well, not so fast. That mind-bogglingly huge number comes with a big asterisk, a really big one. It's based on what we know right now. And this is the nagging thought, the uncertainty that keeps physicists double-checking everything. What if the calculation is wrong? What if there are some unknown quantum effects, some corrections, that could make that countdown significantly shorter?
So this leads to a massive philosophical question. If the universe is living on borrowed time, if it could have decayed at any moment, well, it's been 13.8 billion years. Why are we still here?
Yeah, if the universe could have decayed, why are we here to observe it? It's a heavy question, and it basically leaves us with two profound, totally mind-blowing explanations.
So which is it? On one side, you've got this idea of anthropic selection. Maybe we live in a multiverse, with countless universes popping in and out of existence. The unstable ones? Well, nobody's around in them to notice they're unstable. We find ourselves in this one precisely because it had to be stable long enough for life to evolve and ask this very question. Then, on the other side, you've got the infinite time argument. In a cosmos that's infinitely old and huge, even impossibly rare events are bound to happen somewhere, sometime. We just happen to find ourselves living in one of those incredibly lucky, stable moments. So, are we cosmic lottery winners, or is our very existence proof that the conditions just had to be right?
Now look, this whole investigation is far from over, and this is where I hand the reins over to you, because you can pick up the trail from here.
If you really want to get into the weeds on this, there's some amazing stuff out there. You can read the classics, like Sidney Coleman's own work. You can dive into the nitty-gritty with textbooks on quantum field theory. Or you can explore the bigger cosmological picture. Hey, if you're feeling really adventurous, you could even try to code up a simple simulation of an instanton yourself. The point is, this isn't just a spooky sci-fi story. This is an active, real investigation happening right now at the edge of what we know about the universe.
And that's really what it all boils down to. The Instanton Paradox leaves us with this one ultimate question. Are the laws of our universe set in stone, eternally stable? Or are we just living in a temporary bubble, floating in a much larger, much stranger cosmic landscape we can't even imagine? It really challenges everything we think we know about reality itself.